Okay, so in Calc 3, so this is an extension. So basically day 2 on worksheet 14.5. Okay, now there's no assignment on this, but there is some stuff on the practice final and the final dealing with this stuff, and hopefully too it will help out doing worksheet 14.5 and give you a little bit more understanding of what's going on here. Okay, so basically we're looking at, let's say, maximizing the directional derivative which basically is an interpretation of the gradient. Okay. So basically we just did the worksheet on du, which is the directional derivative, which is a unit vector. Okay. And dot it with the gradient, which still deals with slope, but basically this converts a function into a vector. And the way we do that is by derivatives. So basically going from a position to a velocity and how we write it. Now you can also, provided that if you have angle measurements, it's the same thing. So del F multiplied by cosine of theta. Remember, or etc., that cosine theta is also a unit vector. Okay, that's when we were just doing in two-dimensional. Okay? All right, so outcomes of this. So if you have, gradient F basically can points in the direction of the maximum rate of increase. Can you have a negative value? And yes, and that would be in terms of a rate of decrease. Okay. Other thing is kind of hard to wrap your head around a little bit, but you got to think about what you get as an outcome when you find the gradient. This is always the normal. Okay, to the curve. And basically, people think, well, because you're used to so much for a tangent line, but realize that we are in three-dimensional. So when we are doing this, let's say this is a part on your contour map, and you find a point, and when we're doing this del F, this is a tangent plane. And a tangent plane in standard form is a normal. So there's a plane here that we are finding, and that would be the normal to that. So you got to realize that you're finding tangent planes, not tangent lines. And since we have tangent planes, the normal represents that plane. Okay? And then the other key thing is realize that when you are doing du, that implies a, quote, directional keyword directional derivative. But it is a unit vector. Okay. All right, so let's go through and change up the scenario just a little bit here. Okay, so if f of x comma y is equal to x, e, y. So notice that this is your function. And you need to convert it to a vector. Okay, come on. Now, find the rate of change of f at point p20 in the direction of, let's say, call it Q12. Okay. All right. So notice the word direction. Okay. So that would mean the direction is implied that we're going to go from P to Q, which would be 2 minus, whoops, get that one backwards, 1 minus 2, and 2 minus 0, or negative 1 comma 2. Okay, now that's just the slope, but remember du is a unit vector. So therefore, you have to multiply. So the the magnitude of this be 1 squared plus 2 squared, so root 5. So it'd be 1 over root 5, negative 1, 2. There's my directional derivative. Okay, so now taking my function now and convert it into a vector. So del f of x, y. Okay, so the derivative of x would be e, y, and derivative of y would be x, e, y. Okay, now the point is at 2, 0, so gradients of f of 2, 0. So e to 0 would be 1 and 2. So now putting all the pieces together, so du dot gradient of f of 2, 0. So taking 1, 2 and dot it with negative 1, 2, and put the square root of 5 on the outside. So 1 over root 5, and that would give me negative 1 plus 4. And what I have then is 3 over root 5. Okay. So questions in terms of understanding what I just did here. So if I asked you these type of questions, let's say 1. In what direction does f have the max rate of change? Okay, well, what that solution to that question would be gradient of f of 2, 0, so therefore it would be 1, 2. Okay. Second question, let's say if I asked you this, what is the max rate of change? What piece is that? Well, that would be the magnitude of f of 2, 0. So let's put f's values around there. So what's the magnitude of 1, 2? That would be 1 squared plus 2 squared, so it would be root 5. Okay. Anyway, all right. So hopefully it helped out a little bit, but let's do a little bit more because there's a couple of little pieces I want to add to this. All right. Okay, so let's say if I give you the graph, I'm going to call it C of t because we've been using C, and my vector here by components is sine of 2t and cosine of 2t. Now, if I graph that function out, it looks something like this. I have like an 8. Okay. So this is the rate of change with respect to t. And we can call it as time, as it moves, and it is the particle, as it moves along the curve. Okay. All right, so now the next piece here, let's say the temperature. So the temperature is determined by t of xy, and this, I'll use this function here, x squared y plus 3xy to the 4th. Okay, so notice that this is your function, okay, in terms of how it's written. So as you move along here, there's certain spots that will obviously be harder to turn, where other places like here on straight stretches, say here, be easier. So your temperature is going to change according to how difficult you're moving along this object. So I want to know, how is the temperature changing? So I'm looking for a rate, and let's do it at t equals pi over 2. Okay, so here's my question. Okay, how is the temperature changing at t equals pi over 2? Okay, so this is just what we just did on the previous problem, but in terms of starting to put some values to it. So first off, you have to find the gradient of f. So I got to take my function, and actually it should be t, I guess, gradient of t, and convert it into a vector as a velocity. So of x, y. So by doing that, so doing the derivative of x, I would have 2xy plus 3y to the 4th, comma, x squared plus, what would we have here? Looks like 12y to the 3rd. All right. Yep. Okay. Now, finding values for x and y. So this is where we got to come back. Let's take a look at my c of t here. I have sine of 2t, cosine of 2t. So if I plug in a c of pi over 2, okay, I would have a value of, what is that? Oops. 0 and -1. Okay, so now that's my x and y. So plug that into here. So gradient of t of 0, -1. Okay, so the first one here would be, looks like 3. And the other one here would be, looks like 12. Okay. All right. So now we got to get my directional derivative. Well, my directional derivative is what my vector already is. So I got to just find this piece here. So I got to take the derivative of that. So c prime of t. And that would give me 2 cosine 2t, comma, -2 sine of 2t. And at the value, c prime of pi over 2. That would give me, let me see here, -2, comma 0. Now, I do have to find my directional derivative, so I need my magnitude of this. So 2 squared plus 0 squared would be 2. So my directional derivative would be 1 over 2 of -2, 0. So now we can go ahead and multiply it by my other vector. So find du dot, oops, t of xy. So my direction derivative, 1/2, -2, 0, dot it with 3, 12. And what do we have here? 1/2. So -6 plus 0, -3. Okay, so can you have negative values? Yes, it's less than 0. So basically the temperature is getting colder at that time. Okay. All right. So now let's say if I want to go back and say, well, I want to try it at, say, pi over 6 or pi over 3. Okay, that would mean then I have to redo all this over again with my new values. So is it possible to come up with a general equation? And yes. And this is where a lot of times you see in physics where some people have already done this for you and you just plug numbers in, where you have multiple variables. So let me show you how this is kind of done here. So let's take a look at this example here. So what we do here is ways of find a general equation. Okay. So that way you can just plug in numbers and you're done. All right, so let's say here's my function, f of x, y, and y e to the x. And then here's my vector, and let's say it's the sine of t, comma, cosine of t. Okay, so again, first thing, you got to find the gradient here. So you got to convert this function into a vector, which would be a velocity. So gradient of f of x, y. So the derivative of this would be y e to the x. And another one would be is e to the x. Okay. But we're looking for a general term, not a value. So notice that my x here, gradient of f, I'm going to be plugging in sine of t, cosine of t, into this. So what I have then would be cosine of t e to sine of t, comma, e sine of t. Okay, now I can make life a little bit easy on this. Now I know there's a GCF, so I can factor out e sine of t, and that would leave me just cosine of t, comma, 1. A little bit easier to work with. Okay. All right. So there is my gradient. Okay. My gradient of f. All right, now my directional derivative. Okay, so first thing I gotta do is take the derivative of this. So that would be cosine of t, comma, negative sine of t. Okay, now I need to have the directional derivative, so I need to find the magnitude of this. So square root of cosine squared of t plus sine squared of t. Well, that would be a 1. So basically my directional derivative is this cosine of t, negative sine of t. Okay. So multiplying du gradients of f. Okay, so now we'd have cosine of t, comma, negative sine of t, and dot it with e sine of t and cosine of t, comma, 1. Now what I'm going to do here is I'm going to leave this piece out. So I'm going to have e sine of t. Okay, so now do the dot product. So I have cosine squared of t minus sine of t. And what I have now is a general equation already done for me. So now I can just plug in several values. You want to say time is 1, time is 2, plug it into your y1 and use your tables, and you get multiple answers quickly. Okay. So in my notes on page 5, there's another example of doing something like this, but I'm not going to go through it. You can just take a look at it. But on the bottom of this, I made a little note. So is it possible to have more than just a function and one vector? Can I have a function and two vectors? Yes. So it is possible. So for example, del f, del t. So if I do the derivative of a function, can I have something like g of, let's use a different color here, of h of t? Yes. So what you have would be like, say, f prime, and basically you have g of h of t times g prime of h of t times h prime of t. So yeah, you can do different scenarios, and there's a huge amount of different scenarios you might see. And a lot of times when you look at physics, or chemistry, you'll see that you're plugging more than one value into some kind of function. Okay, so I'm going to go through one example, and this will be the last one, of changing the variables in terms of more than just 2 or 3. Okay, so we're going to go like from 3 to 2 to 1. There's different combinations you can come up with. So the one that I'm going to kind of go with is going to go from a 3 to 2 to 1. All right. So here's my function, f of x, y, z. So I have 3 variables now, of x squared, y, and z cubed. And then I have x equals r squared, y equals rs, and z equals s cubed. Okay. And basically I want you to do is I want you to find del f, del s. Now we're not doing a directional derivative, we're just doing the derivative of f according to s. Okay? So there's no unit vector on this one here. Okay, we're just doing the gradient times, not necessarily the directional derivative, but just that direction only. So we're just doing the derivative piece only. to keep it simple. All right, so first off, we have to take our function, okay, and convert it into a velocity as a vector. So we have to say the gradient of f of x comma y comma z. So we're just doing a derivative of three variables now. So as we go through here, derivative of x, it would be 2xyz cubed. Now the derivative of y would be just x squared z cubed. And then the derivative of z would be 3x squared yz squared. Okay. Now, plugging in our values here, so f as a general equation, x is actually r squared, y is rs, and z is s cubed. Okay, so what would I have here? Well, so it'd be 2, well, x is r squared, y is rs, and z is s cubed, comma. Let me switch to a different color here. Okay, now plugging in here for this piece here. Oops, excuse me. This piece here. So x squared is r squared squared, and z is s cubed. Okay, and then the last piece here, we have 3. Okay, x is r squared squared, y is rs, and s, or z, is s cubed squared. All right, so let's clean all this up here. So we have here, should be 2r cubed, and s 910. Then we have r to the 4th, s to the 9th. And then we have 3, 4, 5, r to the 5th, and oops, let me get rid of that. And s to the 6th, 7th. There we go. Okay, so now we got our gradients of f done. Okay. All right, so now we need to do like our C prime in terms of S though. Okay. So going through the derivative of this, let me change the color here. So the derivative of this, there is no S there, so the derivative of that would be 0. Okay, now derivative of this piece here, there is an S now, and there's only one, so that would be just R. Now the last piece here, now there's an S there, so the derivative of that would be 3s squared. And I said we're not doing the unit vector, we're just doing just the derivative piece only, according to S. So now do gradient of f, dot it with C prime of S, which basically this would be del f of ds. So we have, let's put this, we have 2r cubed s to the 10th, r to the 4th s to the 9th, 3r to the 5th s to the 7th, and we're going to dot it with 0 r 3s squared. Okay, so let's begin. So this times this, that would be 0 plus, okay, multiplying those two out, that would be r to the 5th s to the 9th plus the third piece, 9 r to the 5th s to the 9th. And looks like we have two pieces we can add together. So this would be 10 r to the 5th s to the 9th. Okay. All right, and like I said, we can do different combinations, but that's kind of where we're going to stop. We're not going to get any more difficult than that. So hopefully that kind of wraps your head around a little bit more. There is nothing on this assignment, but there will be something like this on the practice final. Okay, and yes, there will be something on the final. But hopefully it's real intuitive. The only thing is, remember, we're not with our ST. When I just asked this, there's no unit vector, so don't find the unit vector piece